In this video, we're going to look at related rates. So first we're going to express changing quantities in terms of a derivative, usually with respect to time. We're going to find the relationships among the derivatives in a given problem, and we're probably going to use the chain rule to find the rate of change of one quantity that will depend on other rates of change of other quantities. So first we're going to find the derivative with respect to time. Now this is different than when we do dx or dy dx because we are doing this with respect to time. So find dy dt at x is equal to 1 and y is equal to x squared plus 3 if dx dt is equal to 4. So because we're doing it with respect to time, and I'm going to take this equation right here and find the derivative with respect to time, instead of having dy dx, we're going to have dy dt. So t would be our independent variable. So dy dt, that's because I'm taking the derivative of y with respect to t. I'm going to take the derivative of x with respect to t, so that's going to be 2x dx dt, and then plus 0. Now, they're asking me to find dx dt, or excuse me, they're asking me to find dy dt when x is 1 and dx dt is 4. So now I'm going to find dy dt. I have 2, my x value is 1, my dx dt gets replaced with 4, so my answer is 8. For the second example, we are going to find dz dt. So we're going to find the derivative of z with respect to time. So I'm going to take the derivative of z, which is I'm going to use the regular power rules, so that's going to be 2z, and then dz with respect to time is equal to 2x using the regular power rules, then dx dt, and then 2y dy dt. Now, they're telling me I want to evaluate, I want to actually find, what am I asked to find? Find dz dt. I have an xy value, so I can replace, wherever I see x, I can replace with 1. Wherever I see y, I can replace with 3. They're also telling me what dx dt is. That's a replacement of 4. And I have a replacement for dy dt. So I've replaced dy dt with 3. I've replaced dx dt with 4. I have a replacement for x as being 1. I have a replacement for y as being 3. I don't have anything for z. Well, that's okay. I can find z. Now, I am trying to find dz dt, but I have to find z because I need 2 times z. So to find z, I know that z squared is going to be my x squared value plus my y squared value, my y squared being 3. That means z squared must be equal to 1 plus 9, so then z must be plus and minus the square root of 10. So I have 2, and then my z value is, we're going to start with a positive of 10, dz dt is going to be equal to the 2 multiplied by 4, which is 8. And then I have the 2 multiplied by 9, which is 18. So I have 8 plus 18, was just 26. So I have dz dt is going to be equal to 26 over 2 root 10. If my z is the negative, then dz dt is going to be equal to the 26 divided by negative 2 root 10. And that's my 2 answers. It just depends on if I wanted the positive or the negative, and I'd need to know, right? This shape here, z squared is equal to x squared plus y squared, is in 3 dimensions, and it is a elliptical cone. So this is in 3 dimensions, and we will go through these in Calc 3 when we look at 3 dimensions. Right now, though, we're only in x and y with respect to time. So you don't need to know that I have positive and negatives, other than I have positive and negatives whenever I take the square root. Okay, so typically though, we're actually going to be doing application problems, so it'll make sense to have this with respect to time. When we're doing a related rate, the first thing we're going to want to do is draw a diagram and label the quantities that don't change if it's appropriate for the application, and the quantities that do change as time changes. We're also going to specify the rate of change that you are looking for and record all the given information. So what is it that we're looking for? Are we looking for dz dt? Are we looking for the volume changing as the radius changes with respect to time? We're going to try to figure out an equation that involves the variables whose rates you are looking for and what you are given. We're going to do implicit differentiation, typically with respect to time. We're going to state the final answer in a coherent form and specify units. So usually when we get a negative rate, that means that it is decreasing. A positive rate means it's increasing, but that does not always mean that. It could be as it is going toward the origin or going away from the origin. So it just depends on what the original related rate question is asking. Check your units. Your units are going to be a good indicator whether or not you have the answer right or wrong. And also know what you want to differentiate. And lastly, and this is really important, if you're given any kind of constant, don't put it in until the end, right? So it'd be tempting to say, oh, at this snapshot in time, this is the number I'm going to put in. Typically, we wait till the end. So don't plug in any of the constants until you get to the end. Our first example here is we have a tank that is shaped like an upside down square pyramid with a base of 4 meters by 4 meters and a height of 12. How fast does the height increase when water is 2 meters deep if the water is being pumped in? So this is pumping in. So let me show you that I'm pumping water in. Now, if the water being pumped in at 2/3 of a meter cubed per second, that should be a meter cubed per second, this is the dV dt because of the units tell me that it is a volume units with respect to time. So this is 2/3 of a meter cubed per second. So that's a 2/3. I also need the volume of a pyramid. So the volume of a pyramid is 1/3 the area of the base multiplied by the height. And it's really tempting to put in these given quantities. I have 4 and 4 and 12. And I'm like, well, let's go ahead and put those in there. But here's the thing. If I put in my area of my base, which is a 4 by 4, that's 16, multiply that by 12, divided by 3, I'm going to have the volume, but it's going to be a constant. So I'm not going to do that. Rather, what I'm going to do is I'm going to look at the snapshot in time. So I'm going to look at my pyramid on its side. So I'm going to look at it through the side. Now, we know that the total height here is 12. We know that this distance from side to side is 4. At the snapshot in time, I'm going to build this smaller triangle. It's going to have some height. I'm going to call it h. I don't know what that height is. Well, actually I do, but I'm going to wait till I get to my snapshot in time. And then it also has some base b. So using similar triangles, 4 is to 12 as b is to the height of that triangle. Now notice I want how fast is the height changing. So I want dh dt. So that's my want. dh dt. So because I want dh dt, it doesn't say anything about how fast the base is changing at that height. I'm going to take this similar triangles here and I am going to solve for my b. So I have 4h divided by 12 is equal to b. Now, why do I want that? Well, because I know that I have 1/3 the area of the base. So 1/3 the area of the base is going to be 4h over 12 multiplied by 4h over 12. So this will be equal to, for my smaller triangle, is going to be 4h over 12 squared multiplied by 1/3 and then multiplied by its height at that given time. So what I have is the volume now is equal to, I have 16h cubed over, well, actually I should probably simplify this a little bit. Let me simplify before I square out. So 4 will go into 12 3 times, and so I'm going to have h cubed over 27. Now that is what I'm going to use to do the derivative. Now I'm going to take the derivative of that. So dv dt, that's why we started out with those first couple of questions, like how do I do this with respect to time? Now notice that time is not even a variable listed here. It's v and h. But we want to know how this is changing with respect to time. So dv dt is equal to 3h squared over 27. They tell us that dv dt is 2/3. So 2/3 is equal to 3, and then, oh, I forgot. Don't forget, it is dh dt. I got so excited to put my numbers in there and do derivatives, I forgot. Don't do what I just did. Make sure that you put the derivative of the other variable with respect to time. Otherwise, you're going to get two numbers are going to be equal to each other and it makes no sense. Okay, so don't forget that part. Now, h is when we want to know how fast is the height changing when the height is at the snapshot of time 2 meters deep. So I'm going to put in 2 squared there, all over 27, and my want is dh dt. All right, so now I'm going to go ahead and solve for dh dt. So I'm going to multiply by the reciprocal of both sides. I have 2/3 multiplied by 27 over 12 is equal to dh dt. Canceling things down, so 3 will go into 27 9 times, 2 will go into 12 6 times, 6 and 9 reduced to 3 over 2. And so what this is telling me is 3 over 2 feet per second, or meters, excuse me, meters per second. Gotta make sure I pay attention to my units. Meters per second is the change in height with respect to time when the height is 4 meters, or excuse me, 2 meters, and the volume being pumped in is 2/3 of a meter cubed per second. All right, let's take a look at the next problem. So let me just erase all of this, get this out of the way. Sometimes I have skills to move everything all at once nicely, and sometimes I don't. Clearly, this is not one of those times that I do. Okay, so we have a 10-foot ladder is leaning against the wall. At the top of the ladder slides down the wall at a rate of 2 feet per second. How fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? So we already have our picture. And we have, I'm going to call this y, I'm going to call this x, and I am wanting, what is my want? Well, my want is how fast is the bottom moving along the ground? So my want is the dx dt. How is that bottom part of the ladder sliding across the ground? What do I have? Well, I have the dy dt. Now, my dy dt, it's going down the wall. I'm going to consider the point where the wall and the ground meet as the origin. So this is actually a negative number. This is -2 feet per second. And it's getting closer to the origin, so it is decreasing, the distance is decreasing, so that's why it's a -2 feet per second. So units matter and directionality matters. dx dt, since it is moving away from that point of origin, I expect it to be a positive number. Now, what do I have for an equation? Well, this looks to me like that's probably a right triangle. We would hope that the wall and the ground make a right angle. And so this looks like I'm going to use Pythagoras' theorem, which is the x squared plus the y squared is equal to r squared. Now the great thing is that the latter is consistent, so I can actually put my r value in. So I have x squared plus y squared is equal to 10 squared. Now when I take the derivative of that, it's going to be 0, and I expect it to be 0 because the ladder itself, it is not changing with respect to time. The length of the ladder, which is my r here, is not going to change, so I expect it to be 0. Now I'm going to go ahead and do my derivative with respect to time. So I have 2x, and then I have dx dt plus 2y dy dt is equal to 0. So I am wanting the dx dt. That's why I put it in red. I have the dy dt, which I put in blue. I don't have x and y, but I can find x and y when I use the snapshot in time. So I have x squared plus y squared is equal to 10 squared. My snapshot in time is when x is 5. So I have 5 squared is equal to y squared. 5 squared is not equal to y squared. 5 squared plus y squared is equal to 10 squared. So y is going to be the square root, not plus and minus, because y would not be negative, would be 100 minus the 25. So y in my snapshot in time will be the square root of 75. So 2 multiplied by my 5, the dx dt is what I'm looking for, plus 2 multiplied by my square root of 75. And I know what dy dt is. It's a negative 2. And this thing is going to equal 0. Now, when I solve for dx dt, because that is my want, my desire, my dx dt is going to be equal to, because I said that dy dt is negative 2 because it's getting closer to the origin, when I move everything to the other side, I will get dx dt to be positive, which is what I need it to be. And so I'm going to end up with 2 the square root of 75 over 5 as my final answer. What are my units? Well, my unit in the x direction is feet, so this will be feet per second, and that is my final answer. This next example is similar because I'm going to be using Pythagoras' theorem, and again I want to pay attention to what's happening. I'm going to consider this my origin. That means that as A goes toward the origin and airplane B goes toward the origin, those will be negative values. 2 airplanes are flying in the air at the same height. So we're looking at a plane, P-L-A-N-E, so it's like an XY plane. Airplane A is flying east at 250 miles per hour. Airplane B is flying north at 350 miles per hour. If they're both heading toward the same airport, so this is my point of origin, located 30 miles east of airplane A and 40 miles north of airplane B, at what rate is the distance between the airplanes changing? Okay, so this is what I want. That's my R. I'm going to call this X. I'm going to call this Y. So I want the distance between the airplanes, so I want dr dt. Okay. And I know my formula I'm going to use is x squared plus y squared is equal to r squared all day long. I know that my dx dt, that's for my airplane A, this is going to be a negative 250 miles per hour because I'm getting closer to the origin. My dy dt is going to be a negative 300 miles per hour because again I'm getting closer to the origin. Now I can go ahead and do my derivative right here. So I'm going to get 2x dx dt plus 2y dy dt is equal to 2r dr dt. Remember, that's my want. And I'm ready to start putting stuff in, sort of. So I have the 300 miles, negative 300 miles for the dy dt, so I can put that in. I can put the negative 250 miles per hour for the dx dt. I have an x value, 40. I have an x value of 30. I have a y value of 40. I'm missing the r value. So I need my snapshot in time. So I have 40 squared plus 30 squared is equal to r squared. So r is going to be equal to the square root of, it would be 2,500, which is just 20, or 50, excuse me, it'll be just 50. Okay, now I'm ready to put in my snapshots. So I have 2 times my a, which is 30, that's my snapshot. My related rate dx dt is a negative 250. Then my 2y, my y snapshot in time is 40. My related rate is a negative 300. This is going to be equal to 2 multiplied by r, which is 50. And dr, I'm going to actually do that in red, dr dt. Okay, so I'm just going to get my calculator out and I can tell you what dr dt is. So I end up with a negative 390 miles per hour is my dr dt. And that tells me that that rate in which the distance between those is decreasing because it's a negative 390. All right, a 6-foot tall person walks away from a 10-foot lamppost at a constant rate of 3 feet per second. What is the rate of the tip of the shadow that moves away from the pole when the person is 10 feet from the pole? So the first thing I'm going to do is I'm just going to call this y instead of 10. 10 is the snapshot in time, and I'm not going to use it yet. Similar triangles, I'm going to take this triangle, which is 6 as to x. It has this triangle, 10 is to x plus y. Now I'm going to go ahead and multiply both sides by x and x plus y. So I'm going to get 6x plus 6y is equal to 10x. Moving the x to the other side, I'm going to get 6y is equal to 4x. I'm ready to take the derivative. So 6 dy dt is equal to 4 dx dt. Now my want here, by the way, my want is not the dx dt. My want is this entire rate. This is my want. So I'm going to call this the derivative of d with respect to time. The derivative of the distance with respect to time. Now I can find dx dt because I know dy dt. dy dt is the person is walking away at 3 feet per second. So this is going to be 6 multiplied, and it's away, so it's a positive 3, is equal to 4 dx dt. dx dt. And then there's a 4, so I'm just going to divide both sides by 4. So what I'm going to get is I'm going to get 18 divided by 4, which is 4.5, is equal to dx dt. I didn't answer the question, though. I want to know what the derivative with respect to time of this entire length is, because I want to know the tip here, not how quickly the shadow is changing. This gives me the shadow rate, but I know what dy dt is. So this entire d dt, so d of dt is going to be the dy dt plus the dx dt. And so this is going to be equal to the 3 plus the 4.5, which gives me 7.5, and my units are feet per second. And so that is that one. Okay, the radius of a sphere decreases as a rate of 3 meters per second. Find the rate at which the surface area, so surface area, ds for the surface area, SA, I'll do SA, dt is my want. Okay, I have the radius of the sphere decreases, so I have dr dt. I have dr dt, and it decreases, so that's going to be a negative 3 meters per second. And I want my snapshot in time is at r is equal to 10 meters. So I'm going to have to go find the equation of the surface of a sphere. And that is the surface area of a sphere is A, I'll call it S of A, is equal to 4 pi r squared. Oh, well, this is kind of nice. So I'm going to take the derivative, d sa dt is equal to 4 pi multiplied by 2r multiplied by dr and dt. Actually, I want to do all of that in black, I think. Indecision. We gotta love it. So it'll be 4 pi 2r, and then I have the dr dt. So this is going to be equal to 4 pi, r is 10, 2, and my dr dt, which is -3. That means I'm going to multiply all of that. So I have 6 multiplied by 4, so it would be a -240 multiplied by pi meters per second. It's negative, that means that it is decreasing, which would make sense. If the sphere is decreasing, the surface area should be decreasing as well. All right, gravel is being unloaded from a truck and falls into a pile shaped like a cone at a rate of, now my units tell me this is a volume, so this is dV dt. And it's being dropped into this pile, so this is a positive 10 feet cubed per minute. And I probably should have done that in blue. Be consistent, man. So dV dt is going to be equal to 10 feet cubed per minute. The radius of the cone base is 3 times its height of the cone. So the radius is equal to 3 times the height. So 3 times the height. Probably should have done that in blue too. So radius is equal to 3 times the height. Find the rate at which the height, so I want, this is my want, dr, I want dh, I want how the height of the pile changes with respect to time. And my snapshot is at a height of 5. Okay, so the volume of a cone is 1/3 the area of the base times its height. This is the general formula. And because we already have everything in terms of the height, the radius is in terms of the height, then this is just going to be 1/3 the area of the base, which is pi r squared. In this case is going to be 3h squared multiplied by pi multiplied by the height. So my volume is going to be equal to 3 squared is 9 divided by 3. So 3h, actually let me do 3 pi. 3 pi h cubed. Now I'm going to go ahead and take the derivative with respect to time. And I have the dV dt. dV dt is going to be equal to 3 pi multiplied by 3h squared. And I am chasing dh dt. So my dV dt was 10 and it was positive. I'm going to divide by 9 pi, my h is 5 squared. And this is going to give me what my dh dt is. My units, well, my units should be feet per minute. Whatever this is going to be feet per minute. All right, let's take a look at the next example. You stand 40 feet from a bottle rocket on the ground. So this is you, and you're 40 feet away from this rocket. And you watch it take off with a velocity of 20 feet per second. So we're going to go upwards. And this is the dy dt. The reason I'm using dy dt is because it's in the y direction. And this is a given. So this would probably be in blue. So dy and dt, this is 20 feet per second. We want to find the rate at which the angle of elevation changes. So this is what I'm looking for, is I want this theta. My want is d theta dt. Now, I am going to think about which trig function I'm going to use. The trig function I'm going to use is if I have this side and I probably can find this side, and I'm chasing this side because I want the angle of elevation when the rocket is 30 feet in the air. I'm probably going to use the tangent. So the tangent of theta is going to be equal to my y value over my 40. 40 is not going to change. That means my theta is going to be equal to my tangent inverse of y over 40. Now the reason I gave you this one is because this is really similar to, if not exactly like, the ones that we did when we were looking at the angle of elevation in 3 point, I think it was 8 when we did inverse trig function. So maybe 3.8. Yeah, I think it was 3.8. So now I'm ready to do the derivative. So d theta and dt is equal to, now when I do this, it's going to be 1 over 1 plus y over 40, the quantity squared, and then I have to do the derivative of y, which is going to be 1 over 40. But don't forget I have dy dt. All right, so now I can just plug in everything, and then I know I have 1 over 1 plus, oh, wait a minute, do I have the y? And the answer is yes, because I want to know when it's 30 feet in the air. So look at that. So this is going to be 30 divided by 40, the quantity squared, multiplied by 1 over 40. My dy dt was the 20. And then whatever that ever equals, and then my units, because it is angle, it is going to be radians per minute, if that's my time units from before. It's radians per second. So radians per second. And then whatever that ends up becoming to 4 or 5 decimal places. And that's it. It's a quick video, a lot going on. The only way you're going to get good at related rates is you practice. Make sure you bring questions to class, and we will go over any of the ones that you have questions on. See you in class.